here. And what does that do to the total current? It's going to decrease it. So the act of measurement, in fact, implies that you are changing the very thing that's going on. If you decrease the total current, then of course the total current being less means that there'll be less in the very thing that you're trying to measure. So there's a cost of knowing. The cost of knowing is actually to decrease the very thing you're measuring. Okay? So the cost of knowing is that the I2 is actually decreased by the measurement device. So the thing that's being reported when you put the measurement device in is not actually what was going on before you put it in. There's a cost to knowing. The hope is, of course, is that that decrease of what it is before you put the measurement device in and afterwards is so little that you don't care. That's the whole point of measurement, right? Is that you don't want to be a whole wrecking ball. You want to go in there and be as unobtrusive as possible in your measurement, right? So if we were to try to minimize the wrecking ball aspect of the ammeter, should we have it be a small resistance or a big resistance? Small resistance. So for ammeter, we want to have it be a small resistance. That's the key. That will minimize the measurement error. And that is indeed what happens with an ammeter. If you're lucky, these resistance of the ammeter will be on the order of, for a normal thing you might use in lab, like half an ohm. Now, half an ohm is significant if all your other resistors are half an ohm. But if those resistances you're working with are 100 ohms or 1,000 ohms, who cares about an extra half an ohm, right? So again, in summary, an ammeter is a special resistor that measures the current through itself. It has a way of telling you what the current is through itself. You put it in series with a resistor of interest, because then the readout of your device will be basically the current through that thing. And what you do is you hope to make the ammeter a very small resistance so that it doesn't greatly affect the current that was going on there before you put the ammeter in. Okay? Does that make sense? So it is technically true that the current is diminished when you measure it, but the hope is that that's on some decimal place that you don't even care about. Okay? And minimizing the influence to the circuit of measurement. So let's get to a voltmeter. A voltmeter, what it does is it measures the voltage drop across itself. It has no idea what you're intending for it to do. It is going to simply just report the voltage drop across itself. It's not a mind reader, so you have to connect it properly in order for that reading to be useful. And there you're going to exploit the property that voltage is the same in parallel, right? So for instance, if I go over here, I have my R1, let's say R2. I label my equipotential regions A, B, and C. So let's say I wanted to know, like, I don't know why I keep on picking a resistor 2, but let's say resistor 2 is what I like. I want to know what's going on with resistor 2. So basically that means I want to know what is the voltage drop across this one, what is the voltage difference between B and C. So what I do is I connect a voltmeter between regions B and C. Looks like this. So I want to place it in parallel with the resistor of interest. Notice that this does not require breaking the circuit. You're actually adding an extra parallel branch. You're asking what's the voltage drop between B and C, which is adding an extra resistor between B and C. Okay? So that's the big thing you know when you're doing it right in lab. If you're trying to measure current, put a break, and put the thing in the main flow, this does not require a break in the path. So no break in the circuit. Oftentimes, when you have a voltmeter, you have the two wires sticking out of it. They don't even have plugs or clips on there. They have these little spikes. And what you do is you just touch the tube. You just go, what's the voltage drop across here? Okay. What's the voltage drop across here? Like this. You don't need to do any, you don't need to break any circuit to put something into the main flow. You're adding this extra measurement device across things where you want to know the voltage drop across it. So, this again is going to be an effect to the circuit. If I add an extra parallel branch, what does that do to the equivalent resistance? It decreases it. So the total current is going to go up. So I am affecting it. This is one of those occasions where it's really useful to be able to think of series circuits, as I was talking about at the beginning of next time. I have R1 in series with R2 before. Now it's in series with the R2 voltmeter combination. So when I add the voltmeter, what does it do to the resistance of this section? Decreases it. So the voltage drop across this section is actually going to decrease, and the voltage drop across resistor 1 is going to increase. I've changed the ratio of the resistances in series. It used to be R1 in series with R2. Now it's R1 in series with a new resistor, the R2 voltmeter combo. And since that's in parallel, it lowers the resistance of that. Okay? So again, when you go from R2 to the R2 voltmeter combo, that decreases the resistance, and that's going to decrease the voltage drop across that section. So again, you have an effect on this circuit by measuring. So what you're going to do is V2 is going to again decrease by the act of measurement. So if there's one takeaway from how measurement devices work, the takeaway is that the act of measuring will lower the thing you're measuring. That's true for both of these. Notice that the common thread is a decrease. Anytime you measure something, you're actually measuring a value that you've artificially decreased by attempting to measure it. So again, let's think about this. What could we do to minimize this measurement error? Now, would we want the voltmeter to have low resistance? No. If this was a straight wire, this voltage drop would drop to 0. So what's good is that? We measure 0. It wasn't 0 before we got there, but now it's 0. We in fact want this voltage, this extra parallel branch, to be such a crappy option that no one would really want to take it. So we actually want a high resistance. The voltmeter actually has a very high resistance. That makes that extra parallel branch so unfavorable that it gets very, very little current through it. It just siphons off a little smidgen of current that would have otherwise been forced to go through R2. It just says, hey, I got this really, really hard branch to go through. I just need a few little charges and that's it. Okay? This, again, will minimize the measurement error to something that hopefully is okay. Minimize your measurement error. Now, having a high resistance is a lot easier. A typical voltmeter might have resistance in the mega ohm range. So that's a lot of resistance. Unless the resistors you're measuring are also mega ohms, then it's a big, big wrecking ball. So this is something to know. None of you guys are obviously going to become electrical engineers, but the measurement device is only as good as its limitations, right? So this is your typical, you buy for, you can buy a dual voltmeter, ammeter at Radio Shack or whatever the new Radio Shack is. They went out of business, right? So they cost about $15. It's called a multimeter. And it's good to have one around the house. It will measure current for you. It will measure voltage for you. When it's in ammeter mode, it's a very small resistance because it assumes you're going to put it in correctly. And when it's in voltmeter mode, it's a very high resistance, because it assumes, again, that you're plugging it in correctly. So if nothing else, to save the lab instructor a headache, when you're plugging these things in, make sure that you're plugging them in correctly. So common mistakes. Common mistake is to put in a voltmeter in series. Something like that, okay? Now, that is going to be a massive wrecking ball to your circuit. You're just putting a mega ohm resistor in the main flow. What's going to happen to the total current? Going to go up or down? Down, way down. Basically going to shut it off. You just put in a huge resistor in the main flow. So that's no big deal, because if the current, basically you've shut off the current by putting in some huge resistance in the flow, that at least is not dangerous. It just means that you've basically put a bigger obstruction in the flow than you intended. But here's the real big issue, okay? If you put an ammeter accidentally in parallel, you've just put in a tiny, tiny resistance as an extra parallel branch. You've put in a half an ohm or something tiny like that, and you've just given a way better option to go through than the resistor that it's in parallel with. So what's going to happen to the total current? It's going to go way through the roof. You can have a massive current surge. Okay? Yeah, and then you're going to blow the fuse on your ammeter because way more current went through it than it should, and then you have to hang your head and go up to your lab instructor and say, my ammeter's not working, I'm sorry, can you put another fuse in it, okay? They'll have a screwdriver ready and with some fuses, hopefully. I have a huge box of them on my front table when I do these labs, because there's always at least half the groups put an ammeter. My favorite one, by the way, is something like this. So I have a circuit like this, and someone puts an ammeter like this by accident. What just happened there? I basically short circuited the power supply. I basically taken this equipotential and this one and just put half an ohm between them. Massive current surge. You would probably trip the circuit breaker in the whole lab, except for the ammeters thankfully have fuses in them. Okay? So that's when you really have to be watching yourself, is when you accidentally hook up an ammeter, which is a very low resistance, because you're supposed to put it in series with things, and you accidentally connect it like that. All right? So if you're going to make a mistake, put a voltmeter accidentally in series. That just brings the current way down. You have a huge wrecking ball, but in the safe direction. If you do the other mistake, you put an ammeter in parallel, you're going to get a massive current surge. Okay? Are there any questions on that? Okay, so this will close out homework number 3. And then it looks like I have about 10 minutes left. I'm going to go right through into homework 4. Not any huge major change. There's one topic on circuits that, not even introducing a new circuit element yet. Our new circuit element is going to be called a capacitor. Most of your homework 4 is on capacitors, but there's one thing that I left off that might as well have been on homework 3, but I traditionally know it just takes a little long to get to it, so I put it over on the homework 4. It's another method of circuit analysis called Kirchhoff's rules. Kirchhoff's rules. And I'm going to compare it and contrast it against the thing that I started off today with, which is this method of analysis called, which I'll call the method of equivalent resistance. So let me compare and contrast when you would want to use one versus the other. So the method of equivalent resistance is intuitive. Now you might quibble with that, especially while you're getting used to it, but trust me, it is. You, in some sense, are tracking how the current kind of forks and progresses from top to bottom. This is a good, nice feature of it. Kirchhoff's rule is just basically a bunch of math. Obviously, there's some physics and some reasoning behind it, but at the end of the day, it's all about just crunching together a bunch of equations. So this is the downside. The method of equivalent resistances, for the most part, is not symmetric to which variables are left out and which ones are not. Usually for the method of equivalence, equivalent resistance, you have to know the resistors, and you have to solve for the currents and voltages. Now that's obviously not a hard and fast rule, but that's the general gist, right? You need to know the resistances to get the equivalent resistance in the first place. Whereas in Kirchhoff's rules, they're all variables. So any set of knowns and unknowns will do. Any set of unknowns and knowns. Doesn't really matter. They're all just variables. So this is a plus for Kirchhoff's rules. We don't want to be restricted necessarily in what we know and don't know. And then the tiebreaker is that the method of equivalent resistance has a little bit of a hard time with anything but a single battery. A single battery is what allows us to unambiguously track the current flow from top to bottom, whereas Kirchhoff's rules can actually deal with multiple batteries. So multiple different sources of current that are all basically kind of competing with each other potentially. So multiple batteries, that's a nice feature, and a single battery, that's kind of an undue restriction. So this last line is obviously the biggest factor, the biggest single factor. What I expect is that you will probably highly prefer the method of equivalent resistance. You use it whenever you can. But if you see that there's multiple batteries in the same circuit, well, you got to switch over to Kirchhoff's. Okay? So that's going to be basically the rationale for why we have this. And we'll find it's occasionally useful here and there for other purposes, but the main thing is to be able to analyze circuits that have multiple batteries. Okay, so as the name suggests, it's a series of rules. These rules, by the way, are things that we've already known. We just are giving the rules names now. The first rule is called the junction rule. I accidentally called it a junction rule when we were talking about it. Slipped and caught myself. Okay. The junction rule is basically a charge conservation rule, which is a fancy way of saying is that electrons can't appear or disappear in the thin air. So what goes into a circuit has to be accounted for. It has to come out. So an example of a junction rule, let's say I have a fork in a circuit. It's a fork or a junction. I accidentally call it a junction. Fork, junction, same thing. So what we basically have, the junction rule is basically this. What goes in must come out. That's it. That's the junction rule. What goes in must come out. Now that can, of course, take on many different forms. Like for instance, maybe I have the current coming into the junction that I call I1, and then I have two currents coming out, and they're I2 and I3. So in this case, the manifestation of the junction rule would be that I1 comes in, and I2 and I3 goes out. So that would be an example of a junction rule you would write down. Again, this is not new. We actually did that in the last example. That was one of the very things we wrote. We just give it a name, okay? No big deal. The second rule is called the loop rule. And the loop rule makes sure that essentially energy is conserved. So of course we know that energy can't be created or destroyed. It's one of the biggest features, of course, of Physics 1 and physics in general. And so basically the feature of it in this context is that it's impossible to have two different voltages at a given point, right? If we know that it's 5 volts at this point, it can't also be 3 volts. That's contradictory, right? So whatever voltage is at a given location, that's the volt. That's how much energy is available per charge. You can't have two different amounts, right? That's mutual. What do you call that? Contradiction terms. Mutually exclusive. So yeah, exactly. So that's what the loop rule makes sure. So let me give you the general gist of it. The rule says that the sum of the voltage gains and drops around a closed loop has to be 0. I'm not saying that the voltage is 0. I'm saying that the voltage gains and drops have to add to 0 in a closed loop. So here's my example. Instead of voltage, which is more abstract, let's talk about height. Okay? So here you are, sitting on your couch. Let's say you're, I don't know, let's say 100 feet above sea level. So you write that down. And then you go out for a run, okay? So you go out for a run. First, you go up some mountains. Obviously going to be at a larger height. You have a height gain. And then you might go down into a valley or maybe scuba diving or something like that. I don't know, whatever you're into. So that's a height drop, okay? Chances are you don't live, your couch is not below sea level, okay? So you can have all these gains and drops, and then you come home, you're back at 100 feet again. So what's the difference between where you started and where you ended? It's 0. If your couch is at a different height at the end than at the beginning, there was some kind of major seismic event, okay? So that's all we're saying in a circuit is that when you start off at some place and then you go somewhere else and you come back, it's still the same voltage as when you left. There's no, all the gains and drops that you had along your journey have to have canceled back out when you come to 0, okay? So there's no, you guys seen those famous M.C. Escher paintings, right, where all the stairs go downward in the closed loop. That doesn't exist in reality, okay? So this is our way of making sure that happens in a circuit. So if you wander around a closed loop in a circuit, when you return, whatever gains you achieved walking away have to be canceled off by drops upon the return, okay? So what we're going to do, just to give you a little preview, we're going to just write down these equations, as many of these as we can about a circuit. Make sure that the charge is all there. Make sure that we don't have mutually contradicting voltage values at a same location. And it turns out that if you write down enough of those seemingly trivial statements, you can write down so many equations until the currents and voltages and whatever are so constrained that their values have to be that. And that's Kirchhoff's rules. Okay? So a series of trivial statements, and enough of them constrain the values enough that we now know everything we want to know about the circuit. So I'll show you how that works next time.